Okay, welcome back. I think we're recording now. Welcome back to our demo day here. I'm excited. I saw a lot of teams put in, I would say, an exceptional amount of effort. Ideally, it wouldn't be as much last minute effort. I know that's just how things go, that you have to balance other classes and assignments and due dates. But I think you are all seeing kind of the elevated stress that comes with working, Monday night on an assignment due Monday night. And for FPGA assignments, it's hard to avoid those design runs that can take 30 minutes, that can take an hour. And so if you can spread those out a bit more throughout the week, I think you'll be in better shape. So there was a lot you learned, and everyone should feel pretty proud about their accomplishments in MP1. Starting from nothing, uh, taking charge of a pretty complicated hardware software design, extending it, understanding it well enough to really probe both the hardware and software side of it, make adjustments and additions to it, and get something that actually works in the end. I think you should feel pretty good about that, and I feel pretty good about that. So let's get started. We'll get started with team number 6 today, and feel free to get started. And just you can say next if you want me to go to the next slide, or I can just kind of figure it out as we go.
All right. So we're team six. This is a kind of breakdown of the work. Micah did a lot of OpenGL. I did a lot of the hardware part with the VHDL, and then Raphael helped me with that. And then Sam worked on the driver. All right, next. So is Sam here? He can talk about the
Yeah.
driver.
You guys hear me? Um,
Yep.
so the driver, I can't really see the slide, but for the part of the driver, it was pretty simple. We just once I figured out the driver, I talked to Sam, just had to send the driver to the FPGA board or send the XY height and width to the FPGA board through the Ethernet with the send right or send 32. And then for the GLX swap buffers, that wasn't too bad once I again talked to Zambrino and figured out what to do. It just took the back buffer, and if the back buffer was 0, we wanted to send the color buffer of like color buffer 2 to the render output. So that's what they would write to, so we didn't mix up our frames.
Okay.
And then, so this is the viewport. So the viewport obviously does the coordinate transformation from I guess the X NDC, Y NDC to XVP, YVP. So this is just some of our code for it. It uses the FSD that or FSM that Zambino kind of provided for us. And then there's the diagram of it with the breakdown of the stages. I don't think there's anything too special about that.
And I'll jump in here, Josh, and add that yeah, obviously a lot of the starter code for that was provided. And while we talked about Axie Stream sort of in the abstracting class, I think there's no substitute for playing around with it. This is where some of these things can be a little tricky, and teams that had progress towards reasonable test benches, whether it was tickle scripts or top level test benches or other ways of testing, wound up doing pretty well. But your test bench is only as good as the logic you put it in, and so a lot of teams didn't have this line right here. Um, Partially because some of that Axie Stream logic was outside the state machine, and whether that's the right way to do it or not. But some of it was separate from the state machine. Other parts of it were inside the state machine itself. But checking for that T ready signal, knowing that downstream is actually ready to receive the data we want to send before we move on, is an important thing. Otherwise, certain designs, certain code would work, other code would not work, because for the red pixel, it's just sending one vertex through. This signal's probably always high because there's a bunch of FIFOs buffering along the way. But now when you have fractals and you're sending millions of vertices through, this will be high a lot of the time, and other times it'll be low. And it's really somewhat arbitrary when it's high or low. You can't easily predict it. So having a test bench that takes it into account will really help. And if you did that work on a test bench, it can almost wholesale kind of be reused for this upcoming assignment. So I just wanted to add that there, because a lot of teams had this almost entirely working, plus just a little extra handshaking was needed at the very end.
Yeah, I think we did make a test bench for viewport. I don't know if we ever got it working or actually used it for testing, but I think we have the like skeleton of one basically. So we might use that for MP2.
Great.
All right, and then this is render output. So our render output does all the calculations on the ARGB values, multiplying them by 255, and then rounding them as well, and then cutting off all the unnecessary bits to get them down to 8 bits, and then assigning that um, to the write data, and then the address then becomes the pixel. And then it uses that equation down there that is kind of hard to see in the slide. And then this is also another FSM that was kind of provided for us with the states. I think there's 4 states in this one. So yeah, and then we're doing the same thing with the Axi bus, waiting for like the D cache to be ready to receive. And then once it is, then we write the data and update the state. Sam, you want to go on this one?
Yeah, I think Micah's here now. Do you want to talk about your OpenGL program a little bit? I didn't get the chance to look at that. Okay. So the results, Micah made a GIF somehow. I don't know how because I haven't looked at it, but it's pretty incredible. And is this the last slide, or what about the challenges? Is that on the
Yeah, challenges was the last slide.
So let me know if you can't see it. If you're watching the Zoom stream, you may want to just pin my video where I'm showing the slides in the background, or just open up the slides on your own, right, from that same link. So you guys had a slide here for results and challenges. No, results showing. It looks like, though, Josh, I'll ask you, your audio is coming in the clearest. Did you get this fractals looking pretty pixel perfect, or was it still missing some vertical bars along the way?
Yeah, I did get it to look like that. So that's one of the what was it? The FB transmit screenshots from the board. So that's directly taken from there. It was the rounding error that was causing those black lines.
So having this logic here where you just check
Yeah.
that if it's 0.5 or greater.
Yeah, so that fixed a lot of it. I think one problem that we're still kind of facing is there's something wrong with our fern where it's flickering at the top. I don't know what that's about, but I don't think that's too big of a deal.
Yeah, and we talked a little bit about this. So Mike, I don't know if you're online. We didn't hear you. Let me check if you're actually here. I think you're here. This is your GIF or GIF player. Yeah, it says your microphone's unmuted, but we're not hearing you, Micah. So it looks cool. There you go. I mean, I guess there's not that much more to it than you're reading from the file and you're then sending that as pixels to the screen.
Yeah, so he incorporated multiple GIFs that we're able to run in there. And I think it can basically run any GIF as long as you have the GIF file imported.
I kind of like the effect of kind of like the zoom in effect as part of it. So it's using 2 different viewports. Is that how it's? Well, you'll have to explain about that later, because it looks like maybe one way to do it would be to draw the same scene twice with 2 different viewports, and that'd be kind of a cool way to do it. But I wasn't sure if that was the approach you took. Okay, moving on. Well, any questions for that team? Other questions for that team before we move on? Questions for Josh, whose microphone is actually working. All right, excellent. Thanks, team.
Thank you.
Right, group 7.
All right. Yeah, hello, everyone. We were group 7. This is a rough breakdown of how we split up the work. So myself and Nolan did the VHDL design, and then Ethan and Cameron focused on the driver at the start. And then Ethan continued on and did most of the OpenGL work, and we all helped out with debugging, as well as Zambrino and Steve. But
Hi, it's Cameron. I wanted to talk about the driver. So much like the last team, for GL viewport, we used ROID32 and wrote the given X, Y width and height values into memory using the graphics map we're given. And for the GLX swap buffers, we write the current buffer that we got from the get back buffer set active buffer function and use that address to read it.
Excellent.
So our viewport design was very similar to what the last group shared. We used the same basic state machine that was kind of laid out and pass through, multiply your X and Y coordinates, and then add their offsets. And
so can I ask, Riley, is this a diagram that you created because you needed a diagram for the report, or was this something that was useful to have as you were doing implementation? Which one came first, the implementation or the diagram?
This time the implementation came first. I believe we made this after the fact. But.
Yeah, and I understand. I mean, I understand that just from a practical perspective, but I could also see having a diagram like this would make it easy for someone else to then implement it, right? It's a nice kind of breakdown of what needs to happen in each of the states. So that would have been useful to have, but I understand why it, would have come after the fact.
Yeah, and to build on that, we had a similar diagram for the render output is shown. Now, what this dives into a little bit is actually showing a bit between what happened in the state machine and what sort of logic happened outside of the state machine, just in structural VHDL. And so you can see that with like the multiplication. We were facing a few writing, it wasn't quite always consistent. So we moved some of the code outside of the state machine that would be standard, and then just kept assigning the rest of the values within them. So you can see that multiplication for the colors is primarily what occurs outside of it, but it still follows that same mathematical flow that most teams I'm sure did.
And we'll actually see that trade-off a lot in the MP2 code base. There's no hard and fast reason why you want to have logic inside your clocked process versus kind of just data flow logic outside it. I just, if you're adapting code that I provide for you, I sometimes just find it easy to declare the math outside of the project, the process. When I want a multiplier, I just declare that multiplication is happening, and then the process is mostly responsible for setting registers, for determining which registers need to be set and when. So whether that's the right way to do it or not, you could have everything inside the process. You could have everything without having a process at all if you wanted to. But I find this kind of breakdown a lot easier for me to read when I look at the code. Okay, so I have a register. Maybe I have some color coding to indicate registers versus your other color coding here. But I have a register. It's always going to be connected to a signal that's the output of the multiplication. Then when the right things happen, then I set that to another register and continue down the pipeline. There's a lot of that in MP2. So being able to draw these diagrams, whether after the fact or beforehand, I think will really help your team and help other teams who are looking at the MP2 code base, which does a decent amount more of this kind of logic.
And then to switch into one of the first problems we had similar to last time, we noted that there was a few reading comprehension issues within the team, and that did not quite abate this time, though we did attempt to read the document more carefully. The main thing was that we incorrectly read what kind of order we were printing out the colors for the pixels, or rather writing them to the memory cache. And so this actually caused us a delay by about 3 to 4 days in debugging because we couldn't see anything happening on the screen. But we can talk about that a bit more with the next challenge in the next slide.
Yeah, so I'm Ethan, and so these were also, all these challenges kind of played into the same thing, and that was we kind of forgot our memory was word addressable, or it was byte addressable, not word addressable. So one of the big things, like you can see there, is that we had 4 versions of everything on the screen at once. So that was a really easy fix. We just had to multiply by 4. But another part of the issue was that we were reading our color channels wrong. We were starting at the Z and W component instead of the R and G component. And so what ended up happening was we were only running Sierpinski, and that was using the green channel, which was always 0 because we were reading the W component of the vector. So we were trying to figure out why we were putting nothing on the screen, but we were really processing everything correctly, just with the wrong colors. So the math was
I think a
correct,
potential fix for my end is, you may assume that when I assign these labs, I know exactly how it's going to go and what problems you're going to encounter. That one, I didn't expect that particular issue of only setting alpha and having a completely blank screen. If I just change the Sierpinski code to use 2 channel colors, then you would at least see something, and you would know you were close much quicker than if it just turned out to be blank.
We also should have used a different example too. We were stuck on Sierpinski. And then, yeah, as soon as we ran the fractal, we saw the 4 things. And
I guess that would have helped too.
Yeah.
There's been a lot of discussion, multiple teams about what was the right color ordering, and the answer is it's kind of arbitrary, and so you have to look in a few different places to determine what the right answer is for this. And it's a little unfortunate, but that's just how it would go in a driver and in the hardware system, right? There's your application that generally would indicate RGBA order, both the specification of the vertex color array, and once we write vertex shaders, the .r, .g, .b, .a components are assumed to be in that order. Then there's the driver that takes those and actually has to copy those into memory. We could also change the order at that point, right? The driver can set them in whatever order they want to. If I wrote the driver to pass those vertices through and I change the order, that's our new order. Then there's the hardware data structure. That's the third place it can get reordered. We have just that array conversion type or that record conversion type that allows you to specify what order you want things to be in. And then finally, there's the actual VDMA output that spits out to the display controller. And so really at any point along the way, we can kind of mix things up and be fine. So there really isn't actually a correct order. There is an order for the physical signaling to get physical video out. But at any other point along the way, it is up to us how we want to have that ordering to be. So it is a little unfortunate that one possible error case was you were only sending alpha, and so you weren't seeing it. That is a little unfortunate, but there is no right order otherwise. It's whatever we have as combination of hardware and software. So for some of you, you could have just fixed it in the driver. That wouldn't have broken anything all semester long. That would have been just fine. But fixing it so that the driver didn't change, at least your hardware will look the same as everyone else's, and that's a good approach to have too.
Yep. All right. So our results, as you can see, we have a working display. And as we were talking about earlier, the color issue was a little bit of an issue because we also had color channels in the wrong places. So on the top right, you can see we had a red fractal, and eventually, just mixing up the ordering, we got the blue one.
All right, so this was kind of our first OpenGL project, and so we basically made a bitmap reader. We put quite a bit of time into this. Our little Lego Dobby friend, our sad Dobby. So we put a lot of time into that. We got that working, and then we realized you already had a bitmap reader, and so we kind of went back and came up with another idea too. But this one too quick, as you can see down in the lower left, and as you have been seeing throughout all the slides, we went through a lot of iterations with this thing because there was a whole bunch of little binary file reading issues we were forgetting to do. And that was us trying to spin Dobby, which didn't work out. It was actually pretty horrifying. So yeah, that was our bitmap reader. We ran into a weird issue where the code on our computer looked wrong, but the code on the monitor looked normal. But everything else mapped 1-to-1 perfectly. So I'm not sure what we did wrong there, but that's just kind of the way it is, I guess.
Yeah, and bitmap is actually a pretty complicated format. It's more complicated than you think it would be for the different color modes. And so it could be just as simple as how it gets read in, how those channels get populated, and what our hardware does with the channels versus what a quote unquote correct OpenGL implementation does with those color channels. So
yeah, that's fair. Yeah, there could have been something on the NVIDIA card. Yeah.
Right. And bitmap itself as a format allows you to specify unusual things for the color channels and still in theory should work. But I wasn't sure what this image was. I now know. Lego. I thought it was Yoda. That's fine. It's not. They're very similar. Okay.
And so yeah, this was kind of our second little special project, and this one was a little more involved. Basically, we made a software vertex shader. So basically, I created a system where you can interpolate lines from indexes. So as you can see there, all you do is define a set of points, and then you give indexes into that array. So I'd say I want to connect vertex 0 to vertex 3. And then I have a fill lines function that does all of that for me. And so basically it just makes, as you can see up top, 150 points in between any point. And so then I also made a full matrix library for this thing. So down at the bottom, you can see we do have like 3D transformations happening to this thing. So we ended up with an actual rotating cube that you could see on screen. And yeah, that's the fun. You can't tell if it's spinning left or right because I couldn't figure out how to do a perspective matrix. So that's what it looks like.
Yeah, it's overlapping. There's no depth information, obviously, in our implementation either. Did this work on the board? I see the still image here.
I didn't get a GIF of it because I did it pretty late last night, but it is spinning on the board.
Very cool. All right, any questions for Team 7 before we move on to Team number 8? Okay, Team 8, you're up.
Yeah, hi. So we're Group 8. So the people who ended up working on this project were Aaron, Josh, and myself, Bryce.
And Bryce, you're a little quiet. I don't know if you're in the library right now
No,
or
I'm
just
not.
Okay, there we go.
Yeah.
We can hear you
Okay, is
better.
that better? Okay. So yeah, so Aaron did a lot of work on a lot of the project and had a big clue what was going on. Josh helped out with the VHDL and a lot of the debug last night. I came in knowing absolutely nothing and trying to figure out how to get this stuff to work. So if we can move on to the next slide. So yeah, the viewport. So the viewport just sort of is like everybody else's. It seems pretty straightforward, and that sort of caught me actually. I thought it was gonna be a lot harder than it was. I thought I was gonna have to like write the entire state machine myself. So I went ahead and did that. So I had to undo that, and then it just sort of worked in the end. So it's a simple design. So simple designs seem to work well. And then on the render output, we had some issues last night. I know that's really small text, but we had some issues last night with grabbing the bits. So we had to come up with a quirky solution for that to make it work. But in the end, we were able to get all of our like colors and vertices right. So that was really cool. And I'll hand it over to Josh.
Yeah, so one of the challenges that we ran into was we broke our Xilinx 8 at midnight last night, which Team 4 graciously let us use their hardware for that last night.
So I'll interject. Is Xilinx 8 still broken?
I believe so.
Okay, it's good to let me know that. I know that now, I guess, through the slide. Okay, I'll make a note of that. Thanks.
Yeah. Oh. Yeah, and then the other thing is we had some changes on the team. We had a guy drop, and then we added Bryce within the past 2 weeks in this time span of this project. So that was a lot of fun. And then in terms of Git, Vivado likes to make a lot of files, as you can see down there. So you can go on to the next slide.
So a lot of teams are using that git ignore, and it got posted, but it might have been a couple of weeks ago now. And that seemed to be working okay for teams. I saw a lot of different approaches to managing your projects with Git and which file systems and how you're editing. But in general, people seem to have that problem sorted out of telling you're not adding, all those temporary files to your repo.
Yeah, and then as far as results go, we got the Sierpinski working. And we really didn't test much else on it because it was late last night.
Okay. So, it's Group 3 may want to talk a little bit about the Dcache when we get to them, but that is correct by the red pixels. So there is a way we have to actually flush that pixel out so that it actually gets sent to memory to be visualized on the board. But I would think a draw line function wouldn't have that issue. Maybe if you draw a number of lines for it to show up would be the issue, as opposed to just a small line. So it'd be something to test if you have time. If we get Xilinx 8 back up and running, if you can get that to go, that would be great. All right, Group 1, you're up. By the way, everyone seems kind of tired and defeated. I get tired, but you shouldn't feel defeated. I'm really happy with, the teams all getting it working, and we're all kind of on the same page going into this next assignment. So tired, I understand, but you should feel good about what you were able to accomplish, and there's more of it. So there's more coming down the pipeline here, but don't be. Let's cheer up. Let's pick up the mood a little bit here. Let's cheer each other on and celebrate our successes, and not feel like we've been defeated by this class. We're doing great. Yeah, few days off. This is true. All right, group 1, you're up.
Okay, we're group 1. So I'm Braden, joined by Jacob and Nathan. I think Matt was a little bit too defeated by the debugging, so he's not actually with us at the moment, I don't think. But we'll carry on without him.
Yeah, so here are our driver changes. We made the appropriate changes in SGP GLX swap buffers and SGP GL viewport. So in viewport, we added those 4 register rights at the bottom, those SGP _ right 32s. And we added the proper register rights in GLX swap buffers as well.
So for our viewport component, I think it was very similar to most other groups. It was essentially a simple finite state machine that would wait for vertex. Once the vertex was received, it would slowly kind of do each aspect of that transformation one step at a time until finally writing it out. We did run into some slight problems with our viewport. I had accidentally was asserting the signal on the output bus, the same signal, the same clock cycle that we were validating if the T-ready was received. So that was essentially causing us to be delayed by a cycle.
And I wanted to add that even this level of diagram, which really just breaks down the basic states and the math you want to do, while it doesn't provide all of the sort of the architectural detail of the previous team's diagrams, I think it's still very helpful to have. After the fact, it's less helpful, but while you're working on this next assignment, even that level of diagram where you have a mental model of what the states are in the machine and what math it's trying to do, I think will be really necessary for this upcoming assignment. All right, I've said that enough, but even this level, which doesn't show all the wires and where the multipliers are and things like that, that's fine. This could still be very helpful as you try to debug what's happening in this upcoming week.
Gotcha. So this is our state machine for render output. I ended up adding more cycles to it. Just with testing. Initially, we were using model sim to kind of like test everything. And I noticed some things needed extra time to propagate through. I don't know if that was a quirk with just model sim, but I ended up adding some extra states in there just to get everything through it. If you go to the next slide, there's kind of just more of a diagram representation of it and just like the states where everything's going through.
This looks great.
And this is just kind of like a representation of how we got our equation to calculate where to store the color information in memory.
This also looks good. For some reason, the decimal representation bugs me, but yes, that's a good, if you had that model in mind, then the actual render output address calculation becomes pretty straightforward. And I guess for teams who didn't have any mental model of this, you were kind of guessing, and that kind of showed as well. But that's okay too, trial and error and seeing what kind of results you get back out. But once you have this diagram, where it's a little weird when decimal, but where you also have to consider the base address as well, then that gives you your math that you get from there. And so that becomes a relatively straightforward line of VHDL once you have that in place.
Yeah, so some of our challenges were having correct math in our model.
We lost your audio there. So correct math, I heard, but then I didn't hear the rest.
Yeah, I could pick it off.
Okay.
So yeah, we did have some issues with our math correctness. We had to kind of work through that. I think a lot of it was related to precedence issues. We essentially were lacking parentheses in places where we needed them. We also seem to have missed the whole section on our lab report where we had to actually write the driver code. So we thought we had everything all done, and then we're trying it out. And then I think either Steven or Sambrino was like, you guys have to write driver code, We're like, oh no. The next issue we had with our flashing image, that was it was actually a result of some debugging. We'll talk about it more on our next slide. But we had some faulty hardware, and we were trying to debug that, so we ended up swapping our buffers. Yeah, it was kind of interesting.
Yeah.
Yeah, this was kind of an interesting bug. So the slow flash is actually the result of our buffers being swapped, because we thought that that was perhaps having an issue. So when we were running it like this, we were essentially only using the front frame buffer. So we're displaying the front frame buffer and rendering to the front frame buffer simultaneously. So that's why you kind of get this weird drawing effect. And then the whole red color, somewhere there's a fault. I think Zambrino was saying it was either likely in the monitor or the board itself. So that was some
Time will
late
tell
night.
whether it's a inexpensive fault or an expensive fault. It's not your team's fault though, so we'll get it sorted out. And hopefully this week, you probably won't be running any designs on the boards this week, if week one of the last assignment is any indication. But yeah, we have to get that sorted out. So something
Right.
wrong.
And our results. So we ended up having our blue and green colors flipped, and we made the changes, but we didn't want to spend the extra hour building it again. We just called it for the night there. Up there, you can see that was a, I don't know if Jacob is back yet, but that was his OpenGL kind of creative thing where he kind of made like a fireworks show kind of there by drawing circles around.
This is a weird ordering of pictures, I'll just say. So this would have been 2006, I don't know, 2015, and I don't know, 2002. So you got a lot older, and then you went back to youthful version. And this isn't me. I don't know who that is. I don't know if that's reverse image search. I've never owned that suit, nor have I ever been that skinny. So that's someone who has a similar beard and is just very stylish, obviously, but is not me. So.
It was close enough, so we
That's right. Okay, group. Thanks, team. And good work with persevering. Obviously, this kind of issue, I feel like we should have seen it earlier, but the tricky part is you never really know. Since we're remotely accessing it, I thought at first maybe the camera was just buggy. But then when we were actually grabbing the frames, you were actually seeing those. Actually, did we test that? When you grabbed the frames using that frame buffer transmit, was it red or was it everything but the red? Do you recall, or did you not actually get a chance to try that application?
I'm not certain we ever tried it, but I do think that was what was being displayed because I mean,
it's definitely what's on the monitor, because what we did is we even power cycled the board, and like the default design, the Digilant design also had red in it when it like red flashing lines through it. But that would have been good to check. And maybe this is still running on it. I don't know. We can check what's on Xilinx 1 right now. And
it is actually still running.
If it's still going, I'll check that myself. Because if the frame buffer itself is red, that's a capital P problem, right? I don't even know where to go with that. That's a bad DRAM or something like that. If it's just the monitor that's displaying red, then there's still a few sources of error, but at least the FPGA board is probably okay. But we'll see. It's not your fault, so we'll have to get that sorted out. Hopefully before Monday night of MP-2 deadline. All right, Group 2, you're up.
All right. Good morning, everybody. We're Group 2, and Christian and I, Daniel, worked on the driver primarily, and then Ryan and Maggie were kind of working on the hardware design with viewport and render output. And then Christian helped with the hardware design as well. And then I wrote our extremely basic OpenGL application. And then for our driver changes, we kind of more or less have pretty much the same changes as everybody else. In the GL viewport, we're getting the base address for the viewport registers, and then writing the X, Y, width, and height values. And then at the bottom of swap buffers, we're writing the back buffer to our render output. However, for the swap buffers, I think we thought there was maybe more work to be done than there really was. So we thought we needed to wait for the status of vertex fetch and rasterizer to get to 0, but We didn't actually have a rasterizer, so that ended up being a problem when we were waiting for that to be 0. So we had to debug that.
So by the way, I would like that to be in there. I mean, that it kind of hedged the language in the MP1 document regarding, waiting for the frame to be done. I do want you to wait for the frame to be done. It's a little tricky. So checking for the vertex fetch status is nice because that at least means we have no more vertices to fetch, but that doesn't mean you're done. Checking for the rasterizer to be done would also be helpful, except we don't have a rasterizer. So when you read from that component, it doesn't exist. You get a decode error back for what you read, which is not 0. And then ideally, you would also have a component or modify your render output to also have a status register that you could read. The driver doesn't look for one because there's not one by default, but it'd be a very easy thing to add. So there's some sort of flow where you check maybe backwards, back of the pipeline to the front of the pipeline, and if all of those things in that order, or check everything twice. There's other approaches you can take, but something like that is what I wanted. The tricky part is that becomes really hard to debug then, because when any of those aren't returning 0, well, then your whole system just kind of locks up, right? The driver just gets stuck in that line of code. So for most teams, including yours, I just suggest get rid of that for now. It'll lead to some flickering because you'll see some redraw happening, right? Because you'll be swapping buffers before the current buffer's done being rendered into. And other weird effects would come. You'll see like old code sometimes, running on it if you're having animation. But that's better than the alternative of the whole system locking up. So, but it was a good faith attempt at that.
Okay, thank you.
So now we have the viewport math and hardware design. So this is our FSM, and like other groups, it's pretty basic. It's probably the easiest part of this entire project, I think, at least. And I think we spent more time just trying to figure out the different types that there were and like reading the code than actually coding this VHD file. So yeah.
When you start your first internship, you'll discover that's also the case, right? You'll spend days and weeks reading code documentation and other people's code to make your 3 lines of change, and that's how it's supposed to be. Which it's frustrating too, but I think most software developers, I would say, hardware, firmware engineers read a lot more code than they write. The code isn't that hard once you know what you have to write. That's always going to be the case, but that's pretty common.
Yeah.
As for a render output design, we ended up adding a few additional stages just for the handshake with the data cache. One thing that we ran into specifically with render output was that we forgot to multiply and offset our address by 4. So we were seeing the same duplication issue. Ryan will talk about that a little later. And also our entire image was upside down. Once again, another thing that Ryan will talk about. And one key thing that we did in render output that sunk us quite a few hours is that we assigned a signal that we never actually assigned a value to. Therefore, we were writing nothing. Our X NDC coordinates, we actually never pulled them from our input fragment. So therefore, we were actually never picking up any data. So it turns out that our viewport was functioning and our render output was not grabbing anything that our viewport was correctly outputting.
A test bench would have helped probably catch that earlier than later.
We had a test bench, but unfortunately in the test bench, we hard coded in values into those signals.
Yeah.
So.
And I think it's definitely a valid question, and different teams took totally different approaches. To what extent do you want to simulate the interfaces to this versus simulating the logic? And there's no right answer for that. I think there's overhead of having to simulate the AXI light interface to make sure, because that logic should be fine, but to simulate all that. But I think at the very least for this MP2, for teams that are wanting to simulate MP2 and you're going to want to be simulating it, you're going to want to simulate the AXI stream interface, which isn't hard, right? It's T valid, T ready, and T data. You're going to want that to be what you're forcing as opposed to internal signals in the design, because there's a lot more issues with getting T ready low and does it know to stop and pause and apply back pressure. There's a lot more of that because now, right, viewport and render output are just going vertex or fragment by fragment, and there's very little delay associated with it. You could have a very small triangle that has very few fragments, and you can have a very large triangle. They're both the same amount of input data, but a widely varying amount of output data. So the AXI stream stuff becomes critical now versus even if you had T ready wrong or weren't checking mem ac and things like that, yeah, you'd be dropping some things, but it probably looked okay. And depending on the application, maybe you don't even notice it. You'll notice it for this upcoming one. It'll lock up generally if you're missing fragments along the way. So um, simulation is important. Yeah, it's an important question. What are you simulating? I think Axie Stream is probably sufficient where you're setting valid and data and waiting for ready and things like that in your test bench. It doesn't have to be much more complicated than that, but it should at least have that, I think.
But yeah, we can go to the next slide.
You wanna take the rest of my slide, Christian? You took like half my content. So yeah, the first real challenge, or at least the overarching one, is Vivado hated us all, and it kept on crashing not only not only crashing itself, but also crashing the computers we were on. Yesterday we were flip-flopping between every single member's computer because yeah, just constant crashing. As Christian alluded to before, we forgot to assign our T data to the Y pose fixed and X pose fixed. When doing the test bench, we basically just hard coded those signals because we figured it would have been harder to figure out how to use the Axie interface than actually just hard coding this. But now that we understand it, it's easier. When we first got an image on the screen after we finally fixed this, actually outputting data, everything was upside down, which was kind of weird, but Zambrino helped us fix that. Red was blue and blue was red. We figured this out at the end. And basically, jumping to our final point of getting a better camera angle, the one we had, at least for me, because I'm partially colorblind, it was hard to tell that our colors were wrong. So we finally outputted Sierpinski. It was upside down. There were 4 of them. We knew something was wrong, but I was like, hey, we got something. And then everybody on my team was like, but it's red. And I was like, what? But yeah, we flipped things around. We figured out that our coloring or color order, for whatever reason, was BGRA, something like that. It was like flipped. But we fixed that. Then there's also the whole timing thing, or the when you change hardware, it was like 30 minutes, and that's if implementation didn't fail. And then also, yeah, the four of every image, but they were a quarter of their actual size. So we had all of the image. It was just split up into four bite-sized chunks. Yeah, that's our challenges.
And yeah, these are some of the results. On the left, you'll see Daniel's OpenGL application, which is an inadvertent homage to the Cyclone checker of 488. Completely not coordinated, actually. Daniel just kind of presented this to us and we immediately spotted the similarities. But yeah, does anyone else on my team have something to add about these?
So that gray little box there with the little speck, we believe is red dot. We couldn't really tell because the glare on our monitor made it hard to see if,
I think that's a smudge on the monitor.
Yeah, I don't think we flush anything in the driver. So,
but that's awesome. I can't tell you how many hours I have spent looking at the camera and trying to convince myself that there's a pixel there. When, of course, the dirt could be in multiple places. It could be on my laptop's monitor, it could be on the actual camera lens, and it can be on the monitor that the camera is pointing at. That's one of those things. So. It doesn't work for animation, but for grabbing what's being displayed, if you kill your OpenGL application, run that SGP FB transmit, you'll get at least what's in memory, which should be reasonable. So that's pretty cool. I don't think that's the red pixel because it's got like some nice aliasing to it, and it's more than one pixel. That's a nice smudge. I'm guessing, which is pretty cool. I also just wanted to briefly talk about Vivado crashing. We saw a lot of that this week, and I don't think anyone's fault with regards to Vivado crashing. What I would want to know specifically in terms of reports when you say something's crashed, provide a little bit of a report to me so I can start to pass that information on to ETG. I'd want to know, are you on the VDI box or is it your own installation? To be frank, if it's your own installation, it could be you, it could be, it's harder to say what the issue is. But if it's on the VDI box, I really want to know. And for a lot of these, some of the crashes or even just errors seem to be due to some file systems issue. whether it was capacity or just some read-write issue or just some performance issue. We saw that on U drive and X drive. And the other issue that I have seen quite a bit, and I actually just don't know if I'm using it wrong or if it's just a proper Vivado bug, is when downloading and reprogramming a bit file and having the ILA view open. For me, there's a really large memory leak, and it looks like it's just slow and then finally crashes. But if you have the task manager open, you can see that memory leak happening, and it'll use every byte of RAM you can provide for it, and then it'll eventually crash. That shouldn't be happening, but I don't know if I have a project configured wrong or if you're doing something wrong. I'll at least say two things. One, you can discover that it's happening pretty quickly. If the memory spikes up, it's going to eventually crash. At least in my experience, it doesn't somehow recover all that memory and get back to working. What seems to fix it reliably for me, and I also still don't know why, is rebooting either the hardware server or just reprogramming the board or power cycling the board, excuse me. Seems to work reliably the next time I want to program a bit file. I don't know, and it's going to be hard to track down exactly why that's the case. But yeah, that memory leak becomes pretty awful to deal with because it can just lag your entire computer. I got a proper Windows 10 blue screen trying it, which I didn't even think was a thing anymore. Running Vivado. So if you see that happening, it's likely not your fault either. So that's been working for me at least. Rebooting hardware server, exiting Vivado usually, rebooting hardware server, and or power cycling the board, which at least now it's not that hard to do. It doesn't cost you that much time, cost you an extra minute of getting it up and going versus waiting for that thing to lag and crash, which can be very frustrating. So do let me know if you see those other issues, especially on the VDI boxes, and we can try to figure out what's going on with file system at the very least. Anyway, good job, team. We did have for 480 the old version of it, also the Cyclone checkerboard. And then I turned it into a 488 assignment and took it out of 480. This was like 8 years ago. So it's not a coincidence. You'll see bad code written by me in both those classes. Group 3, you're up.
All right, so we're group 3. Nathan worked on kind of render output design, cache flush, and then just spent a lot of late nights working on stuff. Justin and I both worked on kind of the initial viewport design. He also worked on the driver implementation. Was kind of the voice of reason for Nathan in a lot of instances. In addition to that, I made diagrams and usually hosted the VS Code live share. And Savo wrote up our demo code, and he was present for a lot of the debugging.
All right, so here's just the code we wrote for the driver. What's missing from the bottom one is we were hanging the driver because we were checking a status register that didn't actually exist because we were waiting for the rasterizer and the vertex fetch status register. So we couldn't understand why nothing was happening. It was because the driver wasn't actually going through our code. So at the top, it's just the basic, we're setting all the viewport address or the viewport registers. And then, yes, I see that. That's Nathan's comments. Usually his comments are very, very nice to Zambrano, which is why he decided to then go back through and write a bunch of ternary operators there.
I'll let you debate which code is easier to read or understand. Functionally, they're identical. Okay, making fun of my code is fine. I'm not a professional developer, but something to keep in mind for future teams, certainly for MP2 and going forward, when you're seeing your OpenGL application hang, you should be able to sort out what's happening there. Because, and there's a lot of software code underpinning that I know with regards to the driver, but you can look at, how this tracking or tracing of OpenGL calls is happening. And for the most part, what we do is we run the native OpenGL call first, and then we run the driver OpenGL call, the SGP_ version. So if your OpenGL isn't like displaying the screen, which was happening to a lot of teams, it's almost certainly somewhere in the driver in the SGP graphics.c where it's hanging. And that software code, you should be able to debug that. That doesn't require any deep hardware debug skills to understand. Some line of code is hanging in there. It could still be due to your hardware, right? If you get enough back pressure where you're not setting T-valid somewhere along the line and all the FIFO start filling up, eventually it'll fill up all the way back to the Ethernet FIFO. of which are several, but eventually it'll happen, right? It'll fill up that FIFO, and then the SGP write or read 32 call will hang. But if it's hanging and you're not seeing anything on your Linux screen there, that should be fixable, or at least detectable where it's getting stuck in software. So a few teams were seeing that. You'll see that again. Doesn't mean it's not a hardware issue ultimately, but you should be able to know exactly why that's happening, because we tend to run the OpenGL calls first and then run the driver version of those calls. Okay, continue on with your criticism of my driver code.
I don't think there's anything left on that slide.
All right, so for the diagram, first of all, we put a little bit more work into diagrams for this time around because we kind of lost some points last time. For viewport, there's just these two kind of major states. The wait for vertex, where it's kind of hard to read on Sambrino's presentation, but essentially what we do is we just kind of take out the X and Y coordinates out of the SXES T data signal. And then it just goes through a lot of data flow into converting it to the right spots, and then stores it back into the S-axis T data signal at the very end. So a lot of, both for viewport and for render output, a lot of the stuff happening is outside of states, lots of data flow stuff. Inside the states, it's usually just an if statement or two to check a signal and then set the value of a different one.
All right, so I'm gonna pull up the slide that's higher resolution. For render output, we take the input fragment and we do it basically in one state of math, similar to viewport via data flow. So the first state waits for data to come in, and then once that input fragment gets set, and then we store it as the convenient array type, we grab the fixed Q16 versions of X, Y, RGB, and A. X and Y get transformed with some data flow math to generate our memory address. With a similar transformation that someone made a diagram before, so you had to subtract the Y, invert the Y address relative to 1080. So subtract it from 1079. You can see that in the VHDL code at the bottom. And then you multiply by the stride, which right now is a constant. At VHDL quirk, we did 14-bit just so we didn't have to truncate the bits, but it's not important. And then we add that to our X count, so that could see the final address, and then multiply by 4 by shifting by 2. And then also we add it to the base address of the color buffer. The colors, we just multiply by 255. We made a module to do this in that orange arrow. It basically just does what you'd think. We didn't multiply by a Q16 representation of 255, since really the math is the same. So I just didn't want to end up with a 64-bit multiplication output. So we just did some manipulation of the widths of the values to get a 8-bit out result pretty easily. And then the other states are just write address, which is waiting for mem accept signal and the mem ACK after raising the write flags. And then not shown here is when I tried to get our cache flushing working, triggered by the TLAST signal. So there's actually 2 more states, which are very similar to write address and wait for response, that wait for the accept and acknowledgement signals, but they just raise the flush flag instead of the write flag.
So you should be able to see, I know we had a lot of back and forth, and probably 2 late night back and forth, so neither of us were necessarily thinking that clearly about it. That flush should work, and you should be able to see it in simulation. And there's really nothing magical about a frame buffer, right? It's a series of values that are stored in memory that correspond to what was going to be displayed on the screen. So if you saw that writing of the red pixel, which it looked like you were on the ILA, you should then also have the invisible. It could be something as simple as, I would maybe make a version of the red pixel that just freezes after it sends the first frame. Maybe you're not flushing on both the front buffer and the back buffer, and it's actually flickering, and because it's a single pixel, you don't see it. But your logic looked fine for it, and so I didn't have good advice for you other than doing what you're doing. Simulate it.
I forgot to mention as I
confirm it in the
presented
ILA.
here, that even though I implemented the flush, I still never successfully got to see red pixel. So that was a frustration. There's a lot of debugging that didn't see any direction where to go, but I don't know.
All right, so I'll just talk about my OpenGL design real quick. So basically, what it's supposed to do is just create this kind of like rainbow spiral. You can't really see the colors too well from the camera, but you can when we simulate it just in the computer. But basically you take, point, this is all just points. This isn't lines or anything special. You take a point, you just decrement, the theta value and the radius, this isn't like polar coordinates, that is. You just do this a bunch of times and create this kind of spiral. So what you see here to the right is the result of me asking our design to print out more points than my program actually had. And so there's this function called like OpenGL, like draw arrays or something. And I believe I was asking it to draw like 3 times more points than I was actually generating in the vertex buffer. So it was actually generating points from previous programs. So that's what you see there is my drawing. And then I think that's Sierpinski. The little ferns kind of put in different places from a different program.
I feel like that should
yeah.
seg fault though. So it's weird that it didn't. Maybe it's still because you're the only person running applications on the machine, and it's your memory regions that were already allocated, and we never actually free up that memory in the previous running of the code, even though we should. Maybe there's something going on there, but I feel like that should be a seg fault, classic seg fault case where you're just going outside the bounds of your array. I mean, it looks kind of cool. If you intended to do that, I think that'd be a nice effect.
Yeah.
Well, it's a good question. But Aaron, that's a real good question. But there's a lot of things going on there, right? So there's the actual just proper OpenGL driver that would be handling that call to GL draw arrays. I would think that would seg fault for the native machine. But maybe it's the same issue that there's just memory, and it's just able to trawl through memory until it checks the protection bit being set the wrong way, and then it would seg fault. And if that bit isn't set because it's all tagged to you, well, maybe it just works just fine. I have a feeling it would occasionally crash. Yes.
Yeah, because it didn't yell at us at all. So then there's the actual working design. And if someone wants to talk about, there might have been one other bug or / challenge, but if not, that's...
Yeah, I think Justin might have some things to say about that.
He mentioned the hanging in the driver. That was one of the big issues, I think.
Oh, okay, all right then.
Now we're interested on why your viewport looks like that, Reed.
Yeah, so I, like group 7, I also was like, oh, I'll write my own image to viewport code. I did not spend as much time as they did on it, and I wrote it in JavaScript, and it turned out like that. So afterwards, we realized there was other code for
JavaScript.
it. Yes, that's the only meme that we have for this entire presentation is that I wrote the image to viewport code in JavaScript. It just calculates it just comes up with all the the data you put in the arrays into a CSV file, and then you copy paste it over into the C++ file.
But this is a famous piece of like pointillism art, right? So it's really appropriate that it has those kind of like visible gaps between the points. So this is, if anyone ever goes to the Art Institute in Chicago, this is the large Seurat painting they have there. I forget the name of it, but so if it was any other art style, maybe it would look right. I think this almost looks intentional. So
yes, it was 100% intentional.
Okay.
Yeah. Yep.
Great job, guys. All right, team 4.
All right. So for the roles and what we all did, we didn't really have exact things that we did alone. We kind of just did everything together. And we also got a new team member at the bottom there. So yeah, it was a struggle at times, but we ended up getting it at the end pretty close last night. But if you go to the next slide, this is the drivers. And when working on the drivers, we had the right idea, but we were so close, but didn't actually get it correctly. So we were actually writing our pixels to an address that was not used. So nothing showed up on the screen in the viewport. So we didn't know exactly where to look, but then Zambrino helped us out and pointed us there and showed us that was incorrect. But other than that, once we figured that out, it ended up working well. So just mainly what everyone else did for the drivers.
Okay, so our viewporting was pretty much how everybody else did it. I don't think we have anything extremely special to talk about, but you'll see we use those states that were given to us, and we use the signals that were given to us, and then calculated X mult with that logic there. Y mult was the same thing, but with Y's instead of X's. And then we wrote those to memory. One thing that we should probably point out is we did set our output to high, and I believe waited for the response as well here.
It's a nice diagram, though. I mean, again, it's probably diagram done after the fact, and I understand that as well. But breaking down what's happening math-wise and how the states transition is a really nice way to think about the problem that you have to solve. So, anyway, I've said that enough times. It looks good.
Okay, so for render outputs, we did actually have a slightly different approach to a lot of the groups. We were confused at first because the states and the signals didn't seem to line up, and we didn't quite know how to mesh them in place. And we saw a lot of people, moving some signals outside the state machine, or some other groups here added extra states. We just kind of got rid of the signals that were causing us problems and used the original states. So you'll see that in gen address, we set our short reg and our color registers here. And then in write address, we just pull them immediately out and we shrink them and everything right there. So instead of having extra states and having to wait for signals to propagate through, we just skipped a lot of the extra signals. And that worked pretty well. We didn't have to do anything sort of extra to work around that.
Yeah, and there's a trade-off that you'll see. And I'm expecting, so for MP-1, I kind of was really nudging people in this direction. But for MP-2, there's some nudging as well, but you have a lot of flexibility. There's no obvious answer to, how many states should a controller for something like this be? Because there is a trade-off between how much math is happening in a single cycle and how many cycles of latency you're going to have, even ignoring the issue of potentially pipelining it. So even for just a sequential implementation, every team's going to have to face that. You could have done all this in one state, right? You could have, right? Where you just have, or two, I guess, where you have all the data, you do all the math, and you generate the output. But presumably there's a long enough critical path eventually where that for this FPGA board becomes a bad design decision. You'll just have to explore it with that. And teams will have to get functioning logic done in simulation pretty early for MP2 so that they can later worry about issues of meeting timing constraints, which was not an issue at all in MP1. I don't think anyone ran into that at all. It would have been hard to fail timing constraints. In MP2, it will not be hard to do that. So you'll have to get functionality working a little earlier, and then you can kind of play with, well, let's split this up into another cycle and see if that helps things for us.
All right, can y'all hear me?
Yep.
All right, so we had lots of different bugs and challenges. The one that's most recent on our mind is figuring out the color ordering. Yesterday we were basically seeing that was outputting something on the computer monitor, it was like red or something, and then it would show up green on the actual screen. And at one point we had all the colors rotated. So like red was green, green was blue, blue was red. And so we're like, all right, we're going to go in and switch these. And then suddenly our red became like alpha or something like that. And we didn't touch alpha and we had no idea what was going on. And then we ended up flipping everything again and then it was fine. And so we just promised not to touch that code anymore. So that colors were wacky. We also had trouble with the base addresses. So our problem was that we were reading an enum, which was meant to be accessed, or like an array index of an array to get the base address. We were just using the enum, and so we were writing to basically memory address 9 instead of whatever the base address of the viewport was. So we weren't seeing anything, and we're like, why aren't we seeing anything? And then Zambrino helped us out with that, and we're like, okay, so that was a fix. Another thing that costed us a lot of time was figuring out how negative numbers worked. Then looking back at it, we should have probably figured it out sooner, but we're trying to find many ways of writing, negative 0.25 into our viewport for testing. And of course now it's like, you take 0.25 and just take the 2's complement of the whole thing. But we were only taking like the 2's complement of like the full, or the integer part, and then it just wasn't working and we were going crazy numbers and bad calculations. And so we fixed that eventually.
The other way I like to think about that, because I've run into that same issue, is how to store -1 in that format, I think, right? And then you would need to add 0.75 to that. So that's how I would do it personally, because I think it is pretty easy. The simulation makes it a little bit easier because you can see the 16.16 format, but it's easy to get screwed up and spend time testing something where it was just your representation of the hex that you needed for input and output that was wrong, and everything else was fine. So every time you do a simulation, or certainly when you're looking at the ILA, and I kind of mentioned this, but now maybe your teams are seeing this in practice, you really want to have a good feel for, okay, what am I setting as input? What am I expecting to see as output? That's that paper and pencil mode. So that's going to happen a lot, because we're doing a lot more math now in MP2, and knowing what you expect those inputs to be in this format and being able to trace it through that, it's not easy, and I've built it up enough to scare you a little bit about MP2, but that it's not easy. It's easy to get a little lost along the way just because you're off by a bit or you represented something slightly wrong. So having Windows calculator open or pencil and paper, and having a spreadsheet open, and then having simulation open is going to be necessary for parts of this. And even though there wasn't that much math, a couple teams ran into the same issue you had for this one.
Yeah, I remember our major problem was like, all right, we have -1, but how the heck do we write -0? And eventually we got it. So, and then I guess the last thing I kind of have on this slide is, 15 down to 15. I guess it was fine with that. So that was something we had to do to try and get rounding to work. The thing is, so we did have a problem with rounding, which we don't have a picture of it on here, but the right side, like a few of the other groups had the what was it, the fractal, where there was bars on the right side. We tried to solve it by adding the most significant bit of the decimal to the integer part to get it to round correctly. And when we tried it, it actually unfortunately didn't work, but it was already pretty late at that time, so we didn't have time to try anything else.
For what it's worth, teams were definitely able to get some flavor of that to work. So just taking bit 15, if your types are already in that signed or unsigned format, I think you can just add that bit to it. Or you could do an if statement that adds 1 if that bit is high, but it should synthesize to the same. So that's probably a quick fix. When the question is, to what extent teams want to kind of be backwards looking for MP2 or just continue on, and we can discuss that as we go. It looks like every team has a design that's good enough to continue with, as opposed to trying to reverse engineer my new code for that and going backwards in that sense. So that looks very fixable for whatever that's worth. So. Why don't you talk through your demo here?
Yeah. So the demo that we made, we originally tried just to make like a little loading wheel, just I don't know, just out of whatever, and it would seg fault whenever we tried to update the vertices. And so I just kind of took inspiration from Fractal, where it just sent all the vertices and then updated the colors. And so that's what you see, that little color wheel is we generated a whole bunch of points in a circle, and then we just sent updated colors. Unfortunately, this GIF is a bit too short, but it does actually perfectly loop. So it has the seams are hidden. So that was something that we just took a little bit to work on there. But other than that, like I mean, it tests all of the colors, red, green, blue, and yeah, it's just a spinning circle for a demo.
And by the way, not average. Your team did just fine. I don't know. You got it done, and that's what ultimately matters. So I think your team did great. I don't know, and I think the only difference I saw between teams, and every team got it done, so I'm really happy with all the teams, is early preparation versus last minute scramble, and that's that depends on how busy you are with other classes and other things going on in life. It's going to be hard to do last minute scramble for MP2. So last but certainly not least, team number 5. Why don't you, I know some of this has already been kind of talked about with other teams, but why don't you walk through your design here, and then we're done for today.
Yeah, so we're team 5. Isaac worked with moral support and did driver updates. Brian helped with our OpenGL application and also moral support. Alexis implemented our viewport, did some OpenGL and then hardware debugging. And then I did the render output, also a little bit of OpenGL, and then a good bit of hardware debugging also.
I just don't feel like moral support counts unless other teams had members who are actively trying to sabotage the team. I don't know if you get much credit for moral support, but that, or assuming that everyone is providing some moral support along the way. So that's fine. If someone's supposed to be speaking,
Isaac, are you here?
Yeah, Isaac's mic is on, but we're not hearing him.
That's fine. I can take over it. So for our driver changes, like with most of the other groups, they were pretty simple. Basically just passing along some of the different viewport values from our driver. And then we used a simple if-else statement for our swap buffers based on what the back buffer value currently was. And something else with the driver changes that came in handy, as I will talk about later, was we had an off by 1 error in our rows. So we were able to use the driver to debug that versus having to remake our hardware every single time we wanted to debug the issue.
And that's something I had kind of mentioned, Parker and team, that there's just a matter of how much time it takes to make a change and debug something. So if you can change something in your OpenGL application to test whether or not your colors were correct, that's going to be so much quicker than doing a hardware run. And likewise, if there's something in the driver that can kind of fake what the hardware should have been doing, then that's going to be so much faster than making those hardware changes and so forth. So I'm glad you were able to find that was the case for this assignment.
All right, so this is our viewport, pretty much like everyone else, but actually watching other groups, we do not wait for that T-ready flag before we go to wait vertex, but we didn't actually have any issues with that, so that's kind of strange.
But do add that in before MP2.
Yep.
Okay, that's a very quick change for sure. For teams that don't have that, you do want that.
Yeah, and then so as I said, I worked on the render output flow, mostly the same as the other teams, except when it came to the actual computation. Initially, I was having issues with trying to get the values to pipe through the different temporary registers that had come already in inside of wait fragment. So I moved all of those outside. So as soon as we got a new input fragment in, it just piped all those values down to a single temporary signal, which I then wrote to one of the set registers when we changed to the generate address stage.
And something I wanted to add, and by the way, this is a great way to visualize what's happening as well. A lot of teams were taking those software accessible registers as being something really important, that I had some grand plans for all the different software accessible registers. I do want, if you haven't done so already, I do want the teams to take a look at that AXI Lite registers code and see the changes that were made to it. I just renamed some signals that were already in that design and brought them up to the top level ports. Because I think you will find, while the ILA is very useful, if you want to look at AXI signals, the ILA is great for that. You can port all sorts of registers you want and use them for all sorts of debugging things. Something that I think would have saved some teams some time, in retrospect, would be if you had taken this signal or whatever the equivalent of that signal for the address that you were generating and also connected that to a register that you could read from the driver. And then, as opposed to just waiting for the screen to either turn on or the color, right? So as opposed to waiting for the screen to turn on or turn off, you would have a very driver accessible way of just querying the state of your hardware. It's a trade-off. You can do it in the ILA. The ILA provides those hooks to allow you to test any signal as it changes in the design. But in terms of a relatively straightforward way to have a software mechanism to kind of just get runtime debug information, I think for a lot of teams, taking that 2-minute change in the AXI Lite registers, creating a couple more debug registers, and wiring them up to some internal signals in your design will save you a lot of time, because the result was very binary, right? Either something on the screen or nothing on the screen. Yeah, once you got 4 Sierpinski triangles on the screen, you knew you were going to get it done. But up until that point, it was this kind of binary testing result. And that's no good, right? That's a very frustrating place to be in the debugging process. So the more ways you can give yourself ways to learn about what's happening at runtime, the better off you're going to be, the more confidence you're going to be in, off by 1 errors or slight math errors, and just hook up those signals and just read them from the driver and use those same SGP read 32 calls and grab those values. And I think you'll find you'll make faster progress for a lot of teams.
Well, and then here we have some of our challenges. One of the first ones that I ran into was figuring out the correct signals for interacting with the render outputs cache. I ended up going to office hours with Steven to figure that out. I haven't actually used one of the caches in that form. So just figuring out what signals were what, and like figuring out that the mem write, since it's byte addressable, you have to enable it for each byte, was important.
So a problem that I ran into while making the OpenGL was I was trying to define and color way too many pixels for how much memory was actually on the board. It worked fine when I didn't run on the board, but as soon as we ran on the board, it just wouldn't work.
Yep. And then back to that off by one error I was talking about. In our multiplication for finding the memory address, initially we were using 1080 instead of 1079, which led to the first row, the bottom row, actually being on the top of the other buffer. So as I mentioned, in the driver, we just subtracted one row from the value to figure out that that was the bug. And then we were able to use that. And later on, when we were making a few other changes, we added that update to the hardware and fixed the bug.
Yeah, and I like that approach of kind of queuing up or batching up hardware changes. The only downside of that, in my opinion, I mean, there's a lot of upside that, you delay those long latencies of building and testing until you need to, is when you make 3 changes and combine them all together and then things don't work the way you want them to. Now you have to convince yourself, well, which of the 3 changes that I made is what broke things, or, so that there's value in it, but then there's complexity you add where I changed 3 things. I'm pretty sure they were all good, but it's not working. So which of the 3 things, or was it some combination of the 3 things that broke the hardware? So you got to watch out for that. But that's just general, testing issues. In the interest of time, your results look fantastic. And why don't you walk through the demo application you created?
Yeah, so if you just press play.
Oh, let's get rid of the audio for that. Hold on.
We can't hear it.
Okay, fine. Well, I'll have it just blasting in my ears the whole time.
So yeah, it's
You
just
should be able to mute it in the YouTube video.
Yeah, but the stupid settings are messed up. Hold on. All right, we'll view it from here. There you go. Continue.
okay. So it's just Mario. We drew out all the pixels, and then you press L and it changes to Luigi. So
There you go. When you press M, does it go back to Mario?
if you press L again, it'll go back to Mario.
Okay, so kind of Luigi state that you're setting in here. I could see that. We used to have a cool OpenGL demo application for this assignment that would put like 1,000 Marios on the screen, because it would just, those sprites are quite small, so you can actually display a whole bunch of them without any worse performance than, for example, the fractals code. So that'd be kind of fun to bring back out again. And I wanted to mention that, for these applications, a lot of people are talking about, well, it's so slow to send this image to the screen, and the GIF works because it's a really tiny one, and so that's why it's okay. What we're doing is incredibly inefficient right now. We're using the vertex pipeline to send pixels, and that's just not what needs to be done generally. There is a separate pixel pipeline. If I wanted to set the screen a certain color, I wouldn't be sending it via vertices, right? I'd be having the separate pixel pipeline. I'd be doing DMA copies from region to region in memory. So this was just kind of a, learn how to use the infrastructure, get GL points working. But for quote unquote real OpenGL applications, you would never be trying to send thousands or millions of points to try to do anything. You'd be sending primitives, shapes, triangles, and try to do something with that. And that's what we'll see. So the applications you're able to demo are going to get more real world and real world as we go here from MP-1 through MP-4. And this is the most kind of extreme version where to send an image, we're sending 4 million vertices with all the overhead associated with that. And it's so much slower than it would be if we were just copying bytes into memory directly. So great job on the demo day. Teams have to kind of get together one more time, maybe do a debrief on your MP-1 and what worked and what didn't work for each team, and take a look at the MP-2 pre-lab. There's already a couple questions about that, and I'll answer any questions you have about the pre-lab before it's due tomorrow, and I'll also talk about it in lab tomorrow. Try to get a good night's sleep if you can as well, and be ready to go at it again. I'm excited about it, so do your best, and I look forward to seeing what happens and what else breaks for MP2. Otherwise, enjoy, and I'll see you tomorrow.